Hi everyone, I'm Sean, co-founder and chief hardware architect at Cerebras Systems. We started Cerebras with a vision to drastically change the landscape of compute for AI. And today, I will share with you a deep dive into our hardware-software co-designed architecture to meet the demands of ML in the future. For those of you who don't know about us, Cerebras began in 2016, and our mission is to solve the problem of AI compute by building a full AI accelerator solution, from chip to system to software. We now have over 400 engineers with offices around the world. And this August, we were inducted into the Computer History Museum here in Silicon Valley. That was a really proud moment for all of us at Cerebras. And we now have customers using our systems across the spectrum, from large enterprise to HPC and to government. What an incredible journey the last few years have been for all of us here at Cerebras and for the entire ML industry. But we're here today because we're really just at the beginning of what neural networks can do, and we're already reaching a pace where traditional approaches just can't keep up. In 2018, state-of-the-art neural networks had 100 million parameters, and that was a lot. And you fast forward 2 years later, and we got the famous GPT-3 with 175 billion parameters. And there's no end in sight. Tomorrow, we will want to run models with trillions of parameters. Now that's over 1,000 times more compute in just 2 years. Over 3 orders of magnitude more compute in just 2 years. And this is the grand ML demand challenge in front of us all. At Cerebras, we believe that we can meet this unprecedented demand. We can't do it by relying on just a single solution. It has to be addressed by making substantial improvements, order of magnitude or more, across a broad spectrum of multiple different components to meet this unprecedented demand. We need order of magnitude improvements in the core architecture performance, so we can go beyond just brute force flops. We need order of magnitude improvements scaling up. Moore's law simply isn't enough. We need order of magnitude improvements in scaling out to improve and simplify clustering substantially. All of that is required for us to have any hope of keeping up with this ML demand. Is that even possible? It is, but only with an architecture that's co-designed from the ground up, especially for neural networks. And in this talk, I'm going to take a deep dive into the Cerebras architecture to show you how we do this. First, at the heart of all computer architecture is the compute core. And at Cerebras, we set out to architect a core that's specially designed for the fine-grained, dynamic sparsity in neural networks. So this is a small core design, quite literally. This is our core. It's only 38,000 square microns in size, and half of that silicon is used 48 kilobytes of SRAM memory. And the other half is logic, made up of 110,000 standard cells. The entire core runs at an efficient 1.1 gigahertz clock frequency and consumes only 30 milliwatts of peak power. Next, let's take a closer look. First, at the memory. Traditional memory architectures, such as GPUs, use shared central DRAM. But DRAM is both slow and far away when you compare that to the compute performance. Even with advanced bleeding-edge techniques like interposers and HBM, the relative bandwidth for memory is significantly lower than the core data path bandwidth. For example, it's very common for compute data paths to have 100 times more bandwidth than the memory bandwidth. This means each operand from main memory has to be used at least 100 times in the data path to keep utilization high. And the traditional way to handle this is by using data reuse through local caching or local registers. But there actually is a way to get full memory bandwidth to the data paths at full performance. And that's by fully distributing that memory right next to where it's being used. This enables memory bandwidth that's equal to the operand bandwidth of the core data path. And the reason this is possible is, quite frankly, just physics. Driving bits tens of microns from local memory to data path, all on silicon, is much easier than through a package to an external device. So next, let's look at how this memory is designed. Each small core has 48 kilobytes of local SRAM dedicated to the core. And that memory is designed to have the highest density while still providing full performance. And this density and performance is achieved by organizing the memory into 8 single-ported banks that are 32-bit wide each. With that degree of banking, we actually have more raw memory bandwidth than the data path actually needs. So we can maintain full data path performance directly out of memory. That's 2 full 64-bit reads and 1 full 64-bit write per cycle. It's important to note that all of this memory is independently addressed per core. There's no shared memory in the traditional sense. To enable truly scalable memory, all the sharing between cores is done explicitly through the fabric. In addition to the high-performance SRAM, we also have a small 256-byte software-managed cache, and that's used for frequently accessed data structures such as accumulators. This cache is designed to be physically very compact and close to the data paths so that we can get ultra-low power for these frequent accesses. With this distributed memory architecture, we're able to achieve a mind-boggling level of memory bandwidth. If you normalize to the GPU area, that's 200 times more memory bandwidth within the same GPU area, directly to the data paths. Now, with that level of memory bandwidth, we can do some really remarkable things. We can run matrix operations out of memory at full performance across all blast levels. Traditional GPU architectures with limited off-chip memory bandwidth, they're limited to running only gems at full performance. That's matrix-matrix multiplies only. In fact, you can see that any blast level below full matrix-matrix multiply requires a massive jump in memory bandwidth. That's not possible with traditional architectures. But with enough memory bandwidth, you can enable full performance all the way down to AXB, which is a vector scalar multiply. And within neural network computation, this is really important because it enables fully unstructured sparsity acceleration. And that's because a sparse gem is just a collection of AXB operations, one operation for every non-zero element. This level of memory bandwidth is a prerequisite for unstructured sparsity acceleration. But additionally, we need a compute core that can accelerate that sparsity. And the foundation of the Cerebras core is a fully programmable processor that can be made to adapt to the changing field of deep learning. Like any general purpose processor, it supports a full set of general purpose instructions. That includes arithmetic, logical, load, store, compare, and branch instructions. These instructions are fully local to each core, stored in the same 48 kilobytes of local memory as the data. And this is important because it means every one of these small cores is independent. And that enables very fine-grained dynamic computation globally across the entire chip. These general purpose instructions, they operate on 16 general purpose registers, or GPRs, and they run in a compact 6-stage pipeline. On top of this general purpose foundation, we have hardware support for tensor instructions that are intended for all data processing. These tensor ops execute on the underlying 64-bit data path, which is made up of 4 FP16 FMAC units. To optimize for performance and flexibility, our ISA has tensors as first-class operands, just like general purpose registers or memory. And here's an example of an FMAC instruction that's operating on 3D and 2D tensors as operands directly. And we do this by using data structure registers, or DSRs, as operands to the instructions. And our core has 44 of these DSRs, each of which contains a descriptor with a pointer to the tensor, and other key information, such as length, shape, and size of that tensor. With these DSRs, the hardware architecture is flexible enough to natively support up to 4D tensors that could be in memory, or fabric streaming tensors, or FIFOs and circular buffers. Now, behind the scenes, there are hardware state machines that use the DSRs, and they sequence through the full tensor at full performance on the data path. On top of these tensor ops, the core uses fine-grained data flow scheduling. Here, all the computation is triggered by the data. The fabric transports both data and associated control directly in the hardware. And once the cores receive that data, the hardware triggers a lookup of instructions to run. And that lookup is entirely based on what's received on the fabric. With this data flow mechanism in the cores, the entire compute fabric is a data flow engine. And it enables native sparsity acceleration because it only performs work on non-zero data. We filter out all the zero data at the sender, so the receiver doesn't even see it. Only non-zero data is sent, and that's what triggers all the computation. So not only do we save power by not performing the wasted compute, but we get acceleration by skipping it and moving on to the next useful compute. Since the operations are triggered by single data elements, this supports ultra-fine-grained, fully unstructured sparsity without any performance loss. To complement the dynamic nature of data flow, the core also supports 8 simultaneous tensor operations. That's what we call microthreads. These are independent tensor contexts that the hardware can switch between on a cycle-by-cycle basis. The scheduler is continuously monitoring the inputs and the output availability for all the tensors that are being processed and has priority mechanisms to ensure that critical work is prioritized. Microthreading drives up utilization when there's a lot of dynamic behavior by switching to other tasks when there would otherwise be bubbles in the pipeline. With this fine-grained, dynamic, small core architecture, we can achieve unprecedented compute performance, as high as 10 times higher utilization than GPUs on unstructured sparse compute, or potentially even more with higher sparsity. So now, coming back to the grand challenge in front of us, this is how we can get an order of magnitude level improvement from the core architecture. So next, let's look at how we scale that up. Traditionally, scaling up within a chip has been the domain of the fabs. Moore's law has carried our industry for decades, enabling denser and denser chips. And today, Moore's law is still actually alive and well, but it's only giving relatively incremental gains, maybe a 2 times improvement per process generation. And that's simply not enough. So we asked ourselves, can we amplify Moore's law and get an order of magnitude or more improvement? And the traditional way to amplify Moore's law is to make larger chips. So we did that. And we took it to the extreme. This is the Wafer-scale Engine 2, the WSC2. It's currently generally available and being used by our customers every day. It's the largest chip ever built, at 56 times larger than the largest GPU today. At over 46,000 square millimeters in size, with 2.6 trillion transistors on a single chip, we can fit 850,000 cores. With all of those cores integrated on a single piece of silicon, we get some truly mind-boggling numbers for memory and fabric performance, because everything is on chip. And we built a specially designed system around it, called the Cerebras CS2. This was co-designed around the WSC2, enabling the wafer-scale chip to be used in a standard data center environment. It's truly cluster-level compute in a single box. And here's how we build up to that massive wafer from all of those small cores. First, we create a traditional die with 10,000 cores each. But instead of cutting up those die to make traditional chips, we keep them intact, but we carve out the largest square within the round 300 millimeter wafer. And that's a total of 84 die with 850,000 cores, all on a single chip. But all of this is only possible if the underlying architecture can scale to that extreme size. And the fundamental enabler is the fabric. It needs to enable efficient and high-performance communication across the entire wafer. And our fabric does this by using a 2D mesh topology that is well-suited to scale on silicon with extremely low overheads. This fabric ties together all the cores, where each core has a fabric router, and the fabric router has 5 ports with 32-bit bidirectional interfaces in each of the 4 cardinal directions, and 1 port facing the core itself. This small port count enables only a single clock cycle latency between nodes, and it enables low-cost, lossless flow control with very low buffering. The fundamental data packet is just a single FP16 data element optimized for neural networks. And along with that FP16 data, there is 16 bits of control information making up a 32-bit ultra-fine-grained packet. To optimize the fabric further, it uses entirely static routing, which is extremely efficient and low overhead while perfectly exploiting the static connections of neural networks. To enable multiple routes on the same physical link, we have 24 independent static routes that can be configured. We call those colors. All of them are non-blocking between one another, and they're all time multiplexed onto the same physical links. And lastly, neural network communication inherently has a high degree of fan-out, so our fabric is designed with native broadcast and multicast capabilities within each router. Now that we have a scalable foundation, we need to scale it. And scaling within a single die is simple. And scaling beyond the die, what we do is we extend the fabric across those die boundaries. We cross less than a millimeter of scribe line, and we do this using high metal layers within the TSMC process. And this extends that 2D mesh fabric, compute fabric, to a fully homogeneous array of cores across the entire wafer. The die-to-die interface is a highly efficient source synchronous parallel interface. But at this wafer scale, this adds up to over 1 million wires, so we have to have redundancy built directly into the underlying protocol. And we do that with training and auto-correction state machines. With these interfaces, even with defects in the fab process, we get a fully uniform fabric across the entire wafer. Now, these seemingly simple short wires, they're a big deal because they span less than 1 millimeter of distance on silicon. When you compare that to traditional SerDes approaches, the difference is massive. And it's just like the memory, it's just physics. Driving bits less than 1 millimeter on chip is much easier than through a package, connectors, PCBs, and sometimes even cables. And this results in orders of magnitude improvement compared to traditional I/O, as you can see from the table. We're able to achieve about an order of magnitude more bandwidth per unit area and almost 2 orders of magnitude better power efficiency per bit. And all of this translates into unprecedented fabric performance across the entire wafer. If you normalize to GPU equivalent area, that's 7 times more bandwidth than GPU die-to-die bandwidth in the same GPU area at only 5 watts of power. At this level of global fabric performance, that's what enables the full wafer to operate as a single chip. And that's important because with such a powerful single chip, we can solve some really large problems. It enables us to run extremely large neural networks all on a single chip. The WSC has more than enough performance and capacity to run even the largest models without partitioning or complex distribution. Now, this is done by disaggregating the neural network model memory weights and the compute. We store all of the model weights externally in a device called Memory-X, and we stream all of those weights onto the CS2 system as they're needed to compute each layer of the network, one layer at a time. The weights are never stored on the CS2, not even temporarily. As the weights stream through, the CS2 performs the computation using the underlying data flow mechanisms in the core. Each individual weight triggers the computation as an individual AXP operation. Once each weight is complete, it's discarded, and the hardware moves on to the next element. Now, since the weights are never stored on the chip, the size of the model is not constrained by the memory capacity on chip. On the backward pass, the gradients are streamed out in the reverse direction back to the Memory-X unit where the weight updates happen. So let's take a deeper dive into how the computation is actually performed so we can see how the architecture properties uniquely enable this capability. Neural network layers boil down to matrix multiplication. And because of the scale of the CS2, we're able to use all 850,000 cores of the wafer as a single giant matrix multiply array. And here's how that works. For transformer models like GPT, activation tensors have 3 logical dimensions: batch, sequence, and the hidden dimension. We split these tensor dimensions over the 2D grid of cores on the wafer, as you can see in the picture. With activation stored on the core, where the work is actually being done, the next step is to trigger the computation on those activations. This is done by using the on-chip broadcast fabric. That's what we use to send the weights and the data and commands to each column of cores. Using the hardware data flow mechanisms, the weights then trigger the FMAC operations directly. These are the AXP operations. We start by broadcasting the row of weights across the wafer. Each element of the row is our scalar. Within that row, there are multiple weights that map onto a single column of cores. So when there's sparsity, only those non-zero weights are broadcasted to the column of cores, triggering those FMAC computations. We skip all of the zero weights and we stream in the next non-zero weight, and this is what produces a sparsity acceleration. The weight value is multiplied by each of the activations and added into a local accumulator which resides in the software-managed cache. The fmac compute is performed using a tensor instruction with the activations as a tensor operand. Once all the weights for the row have been received, each core contains a partial sum that needs to be reduced across the row of cores. And that reduction is then triggered by a command packet broadcast to all the cores of each column. Again, using the data flow scheduling mechanisms, once the core receives the command packet, it triggers the partial sum reduction. The actual reduction compute itself is done using the core's tensor instruction, this time using a fabric tensor as operand. Once it receives the commands, the core communicates using a ring pattern on the fabric, which is set up using the fabric static routing colors. And using microthreads, all of this is done in parallel with the fmac compute for the next weight row, which started at the beginning of the partial sums. Once all the rows in the weights are complete, the full gem operation is done, and all the activations are in place for the next layer. All of this enables neural networks of all sizes to run with high performance, all on a single chip. That's made possible by the unique core, memory, and fabric architecture. This means extremely large matrices are supported without blocking or partitioning. Even the largest models with up to 100,000 by 100,000 map-mul layers can run without splitting up the matrix. When you bring this together across the single WSC2 chip, this results in 75 petaflops of FP16 sparse performance, or potentially even more with higher sparsity, or 7.5 petaflops of FP16 dense performance, all on a single chip. Now bringing this back to the grand ML challenge in front of us, this is how to achieve an order of magnitude level improvement in scaling up. Now let's talk about the last component, cluster scale-out. Clustering solutions already exist today. So why is it still so hard to scale? Let's look at existing scale-out techniques. The most common is data parallel. This is the simplest approach, but it doesn't work well for large models because the entire model needs to fit in each device. To solve that, the common approach is to run model parallel. This splits the model and runs different layers on different devices as a pipeline. But as you can see, as the pipeline grows, the activation memory increases quadratically to keep the pipeline full. To avoid that, it's also common to run another form of model parallel by splitting layers across devices. But this has significant communication overhead, and splitting individual layers is extremely complicated. Because of all of these constraints, there is no single one-size-fits-all way to scale out today. In fact, in most cases, training massive models requires a hybrid approach with both data parallel and model parallel. So although scale-out solutions technically exist, they have many limitations. And the fundamental reason is simple. In traditional scale-out, memory and compute are tied to each other. Trying to run a single model on thousands of devices turns the scaling of both memory and compute into distributed constraint problems that are interdependent. And here's the result of that complexity. This graph shows the largest models trained on GPUs over the last few years and the different types of parallelism used. As you can see, as the models get larger, the more types of parallelism is needed. And this results in a tremendous amount of complexity. For example, you can see that the level of tensor model parallel is always limited to 8, because that happens to be the number of GPUs that are typically in a single server. And as a result, the majority of parallelism in these very large models is actually pipeline model parallelism. But that's actually the most complicated because of the memory trade-offs. So training these large models on GPU clusters today requires navigating all of these bespoke distributed system problems. And this complexity results in longer development times and often suboptimal scaling. On the other hand, because the Cerebras architecture enables running all of these models on a single device without partitioning, scaling becomes easy and natural. We can scale with only data parallel replication. There's no need for any complicated model parallel partitioning. We do this with a specially designed interconnect for data parallel. This is called SORM-X. It sits between the Memory-X units that hold the weights and the CS2 compute systems, but it's independent from both of them. SORM-X broadcasts weights to all CS2s, and it reduces gradients from all CS2s. Internally, SORM-X uses a tree topology to enable modular and low overhead scaling. And because it's modular and it's disaggregated, we can scale to any number of CS2s with exactly the same execution model as a single system. Scaling to more compute is as simple as adding more nodes to the SORM-X topology and adding more CS2 systems. And that is how we address the last component of the grand ML demand challenge, to drastically improve and simplify scale-out by an order of magnitude or more. So now let's go back to where we started today. In the past couple of years, we have seen over 3 orders of magnitude greater demand from ML workloads, and there's no sign of slowing down. In the next couple of years, this is where we'll be. We asked ourselves, is this even possible? At Cerebras, we know it is, but not by using traditional techniques, only by improving the core architecture by an order of magnitude with unstructured sparsity acceleration, only by scaling up by an order of magnitude with wafer-scale chips, and only by improving cluster scale-out by an order of magnitude with truly scalable clustering. With all of these, that future is achievable. Neural network models are continuing to grow exponentially. Few companies today have access to them, and that list is only getting smaller. With the Cerebras architecture, by enabling the largest models to run on a single device, data parallel only scale out, and native unstructured sparsity acceleration, we're making these large models available to everyone. Thank you very much.